Hello, everybody. So it's fascinating to see the number of talks about the human brain. I will just continue on that. I mean, it's the reference implementation for natural language processing, and therefore one of our inspirations in trying to figure out how to handle natural language text data, basically. So Cortical.io is located in Vienna, Austria. We basically do two things in the same time. One is that we work on the theory side, so we're very strong believers in a theoretical approach, helps a lot to get experimentation focused. And on the other side, we develop technology that all of you who have to work with text data could possibly use in their day-to-day work. So what is the fundamental problem we have to handle when we try to understand what, not we, the computer actually has to try to understand surrounding text. So typically a computer knows how to handle numbers. It's all about processing values. But the problem starts, what is the value of cat? So this ends up being what we call a representational problem. How do we represent the value for cat? And the solutions we have so far are mostly of the sort of statistical modeling kind. So there are all sorts of approaches that try to create models about the meaning in text. We work with word frequencies, vector space models. There is Zipf's law that tells us about the distribution of the frequencies of words in a natural language. And we have all sorts of modeling techniques, and they all work more or less well because language has a lot of statistical aspects, but the problem is it's not purely grounded on statistics, but it's grounded on real data in the real world, and that basically shows already the first problem with processing it, is that we have to find a grounded representation. In a very similar way how the brain is actually doing this. So that's a very nice quote I found on a blog that basically tells you about the difference on how computers work and how brains work. So in fact, they are pretty different. So the computer programmers, in the sense, that's where the intelligence of computers comes from, try to define the general, that's what we call the program. And based on this program, we then basically store the specifics, the data that we capture or that we input into the memory. And the brain actually works exactly the other way around. The brain can just sample data, special case data that it gets in reality. And what we constantly do when we think and when we deduct something or when we predict something is to find the general based on this collection of specific data. So here you see a very standard way of, I mean, might be old-fashioned, but just for the sake of the argument, a standard way of pre-processing data. Just imagine a document that gets sampled to basically become indexed in a search engine. So it has to be pre-processed to accommodate the model that we use. And what you can see is that from the tail, little Snow White, the outcome is something that is hardly understandable. So that's basically how a search engine currently interprets a piece of text, and therefore the semantics in this text. This leads to a problem that, as a very prototypical case, the large search engines face, namely that the more data there is, the harder it becomes to actually find documents just based on the contained keywords. Here you see that you have some inner circle that basically looks all, or circle, it's a octagonal shape in that case, that represents what we assume to be the visible internet, but we can see also on the other side that there are blind spots. So the blind spot basically is the situation where you can take any possible imaginable combination of keywords and make a search using those. And you will find out that there is a large percentage which is in fact proportional to the overall number of documents, which can never be seen, never be retrieved. And the more data we get, the harder it becomes. And the only way around this is to extend the features that we have through the keywords by bringing in semantics. And that is basically what all these big search engine providers do, is they add a lot of specifics. So when they detect a date or when they detect the name of a flight, they interpret a query more specifically, so they bring in semantics. But of course, as you can imagine, the cases and the documents and everything gets more and more, so it's pretty hard to keep up with this special case approach. So our work basically on the theoretical side is based on another theory that was developed by Jeff Hawkins, a neuro researcher in the US. What he's about to do is to find out the processing algorithm of the human neocortex. So he's using neuroscience data, facts that neuroscientists find in their research, and he tries to find the computational mechanisms on how the neocortex actually processes this information and what it does while it processes that information. We have used the theory. You can read his book on intelligence, which is really fascinating work. We used this theory that he created to basically extract some sort of constraints out of that. And we said, okay, if that is the general algorithm by which the neocortex works, and if the neocortex is actually the source of our language capabilities, then everything related to language should also comply with these constraints. So we created a processing methodology that we call Semantic Folding. And it's based on neuroscience and not on statistics, so we don't try to model anything, but we try to actually work with real data, with language data, how it would be perceived by a human. And we use it, of course, in an unsupervised manner. That's the whole point. Yeah? We want to be more effective than manually annotating data and arranging data through human effort. And we try to replace the statistical, the probabilistic approach to language processing with what I call the analogical approach. So we try to find similarities and base all of the language understanding on this. The constraints, there's quite a list. Just the most important things is that the brain is a modular assembly that has sort of a two-dimensional sheet that covers basically the whole brain. The 2D aspect is important, as we will see in a second. Something that is maybe a bit astonishing is the neocortex doesn't seem to be a processor. It rather is some sort of processing memory. And it learns patterns and the sequences of those patterns. And it is exclusively trained by being exposed to data. So there is no a priori knowledge about this. And the key issue is that every piece of data that reaches the neocortex has the same format, a format that we call a sparse distributed representation, which basically corresponds to very long binary strings, which are, as we will see, a very effective way of processing data. So this has even been backed by some neuroscience work. So the whole concept of representing meaning as a distributed pattern in the neocortex has been shown to actually happen in the brain. So there is earlier work from Mitchell who showed not only that they could compute based on fMRI pictures what word a person has heard, but that this even worked across people. So the system could be trained on one person and it would detect the meaning of words based on pictures of the fMRI of another person. This one we saw earlier in the talk before. That was basically demonstrating that for the perception and the understanding of language, the whole neocortex is actually used and not, as we thought for a long time, just very specific areas. So what we do is we simulate a patch of neocortex, and we say that this, let's assume that this is the location where the meaning of word is represented as soon as it is perceived. We do what every human does, we learn, so we have to train the system also in the same sense of learning. So we expose it to utterances. Here, for example, we get the utterances from Wikipedia, but it could be anything. We parse that, we pre-process it, we cut it in little pieces as if we would hear the utterance from another individual. And what we then create is we create a semantic map that basically distributes those utterances over a 2D space. And the 2D is, of course, because it has to fit on the neocortex. When we have computed this semantic map, this is a one-time process basically that starts before you actually use the system. After that, we can generate what we call the semantic fingerprints out of this mapped distribution, and in the pattern that we basically fold into every representation, that's why the name semantic folding comes in, we generate these bitmaps, which are in reality binary vectors, and they have certain properties. So the engine that we have created fundamentally converts every piece of language into what we call a semantic fingerprint. So here you see a couple of semantic fingerprints. In the center you have the word organ, and the word organ has of course several meanings. And the interesting thing is that we can actually see all the meanings of the word organ simultaneously here. We have a region, due to the semantic segmentation of the map behind it, that overlaps obviously with the word piano. So organs can be something similar to pianos, but in the very same time, you see that another region actually overlaps with the word liver, which is another meaning of the word organ, in the sense being an anatomical aspect. There are also, as we can see, cultural aspects like church. Many organs are in churches. But the key learning from this is that every word basically is defined by all the possible contexts it can be used in, and it is simultaneously represented, and the representation has the folded-in mapping of what we've heard so far in our life, or what the system in our case here has been trained on. So what can this be used for? We can, for example, start and create aggregated representations. So the nice thing of having a sparse binary representation allows us to aggregate the sparse vectors without actually losing information. That's one of the reasons why the brain, and in the same way we are using sparse representations, is because we can aggregate them. And that when we aggregate them, we can create a fingerprint that has the same topology for a sentence, and we can therefore make a sentence comparable to a word. And what we do is we measure the overlap between the two. So we actually take one pattern and the other pattern, and we count the number of pixels that overlap, and that basically directly corresponds to the semantic similarity we have between the two. But we have another measure, which is pretty important, is by looking at where the overlap happens, we find out which is the context, what is the topic on which those two words actually relate. If I change this sentence to a sentence that is unrelated, we see immediately the dropping of the overlap. And here you see the specifics depending on where and what I use to train. A word from the medical environment, for example, gets a very sparse interpretation if trained on Wikipedia. If I use medical data to train the system on, I get a topologically very similar representation. So the upper fingerprint is basically contained in the lower one, but the lower one has much more detail, semantic detail. Interestingly, this even works across languages. Remember, this is supposed to be the representation that actually happens within the brain. So if an English speaker hears the word cat and the French speaker hears the word chat, they have both the same inner picture. And what we see is that regardless what language we take, we create always the same fingerprint. Very useful if you want to compare two pieces of text in two different languages without actually translating it. Another very important aspect that makes this different from the statistical modeling approach is that every single feature is inspectable. We can actually go and see that a certain pixel that basically overlaps for two representations contains concrete words about the context of this overlap, and therefore becomes actually inspectable, which in practical terms is very useful because we can actually debug an application by looking into the specific features that are used. We can do things like computational disambiguation. I can take the word organ. I say, what is the fingerprint that most overlaps with the word organ? What is the word for that? And I get the word liver. Then I say, okay, let's take all the dots, the liver dots away from organ and ask again, and what is now the most similar word? And I get piano, and so forth, which basically means that I can, in computational terms, disambiguate any term, any sentence that I have to work with and find out what meanings are there. We can do classification. The classifiers don't even need to be trained. They just correspond to a fingerprint that stands for a certain class of fingerprints. So here we have the fingerprint for mammal that we created by just anding together mammal, mammals, and mammalian. And what we see is that actual mammal fingerprints, all of that has been trained on Wikipedia or zoological data, of course. We find that the pixels of our classifier are most frequently overlapping with the actual mammals and much less with the non-mammals. I can use this to actually create search engines. So by creating a fingerprint for every document in a collection, for creating a fingerprint for the input text, and then just comparing how much is the overlap. And I can even use preferred data, examples that come from the user to improve or individualize the ranking of the results that we have here. We can extract keywords, but the extraction of keywords here is of course not statistical, but it's a combination or a formula that basically says what is the smallest number of words that allow me to recreate a fingerprint from the text that they have been extracted from. So what are the pillars, the semantic pillars of a piece of text? Here another very practical function is to slice. So you have a long text and you want to slice it into little pieces that always contain one specific topic. So you can do this by computing the change from one word to the next word in terms of fingerprints. So this, just to compare this with more traditional statistical modeling techniques, for word embeddings specifically. And one thing, I mean, I don't go into detail here, but one thing that strikes is that the approach that tries at least to be very similar with what the brain does has the big advantage of simply being much more efficient. And that's how we know the brain works in general. It's so impressive because it's so efficient. Technically, this is integrated into Spark. So if you have already tried to use the machine learning library of Spark, you can basically use the Retina engine in the very same way and in the same environments. The products, we have two products which are targeted at the enterprise. One is, of course, the search application, and one is the filtering application. And then we have RESTful endpoints for more play around, so to say, applications where you can basically just take any source of text. You can take the LinkedIn profile of a person and you can compare it to the synopsis of an Amazon book and find out basically which book would fit to what kind of reader. Maybe in lack of the time, I will just show you one practical application, which is filtering tweets out of the fire hose, for example. So let's assume you want to get all the tweets from the fire hose that somehow speak about mobile phones. What you normally would do is you would create a catchword list. So if one of these words is in the tweet and the tweet is about mobile phones, you probably end up with several hundred of those catchwords. And of course, you would have to do some sort of string matching, which basically leads to millions of string comparisons, making the whole approach extremely expensive. What we do is we basically convert every incoming tweet into a fingerprint, and we have one fingerprint that was generated by simply saying, give me the fingerprint for mobile phones, and according to a certain overlap, I will select the messages. That actually I was able to run on my laptop, just to give you a feeling on the efficiency of that approach. The same thing is, of course, applicable also for news and similar applications. I don't know how many seconds I have left. Here you have an example. I just browsed through that at high speed, fingerprinting LinkedIn profiles, for example, or fingerprinting product descriptions, topical analysis of mail conversations. All of that always applies the same algorithm and the same method to convert the relevant parts into fingerprints. Here we see that very similar words keep having the same fingerprint. We have made topic clustering from captions from TV shows, finding out what are people in real time talking about on the TV. How can we optimize findability on Google? We just make the fingerprint for our web page very similar to the fingerprints of web pages that have been nicely ranked by Google. We can detect authors and this with a very small set, so like 4 or 5 examples per author. We can find out from an unseen document who might have been the author. And maybe as last thing, sort of an outlook, we have, of course, also used our system to feed text data into the Numenta network. So Numenta is the company of Jeff Hawkins creating this cortical processing algorithms. And what we do here is we do semantic anomaly detection. So we try to find out in a stream of text if the topic suddenly changes. And we have applied this to the US presidential race and could actually see, I mean, I'm not an expert in US politics, but I've been told that there is a very strong correlation whenever a candidate started to say something unexpected or switch topics of his commands, there was an anomaly detected. Okay, that was the high-speed fly through semantic fingerprinting. Thank you.